All right. So this will be lecture 7, I want to say. At least that's what I have written down in my notes. I could be wrong. Uh, and today we're going to talk about power series, which is basically an entire chapter in Gamelin. And for some reason, I put this on the schedule as something I could tackle all in one day. The chapter includes analytic continuation. So we're actually going to split it in two pieces. The analytic continuation part's going to come next week. But we're going to end on the uniqueness theorem. Has a name. I think it's called the identity theorem. Okay. It also goes by the uniqueness principle. But it is one of the more important results uh, in this portion of the book. Okay. So first things first, we haven't talked about power series explicitly yet. So let's define, oh, let's define, let's take a sequence of complex numbers and fix a point in the complex plane and let C be some arbitrary point in the complex plane. Then something of this form is a power series centered at Z0. So technically, I need to tell you what all the symbol means, right? Uh, I'm going to assume that we understand that infinite series are supposed to be the limit of the partial sums, right? And we understand all the analysis that goes along with that. Uh, so same thing happens here. We can define something called a power series, and this thing turns out to have some pretty interesting properties in complex analysis. So just a quick note, if we sub w equals z minus z0, then we can always reduce this to a power series around 0. So basically you're shifting the origin, which is fine. Okay, so let's jump right into a theorem. Let the sum over k, ak, z to the k be a power series. Then there is a real number r, which is positive or at least non-negative. And I'm going to use this less than or equal symbol here. R could be infinite, such that the power series converges absolutely if the modulus of z is less than r, and diverges if the modulus of z is greater than r. Notice I don't consider the modulus of z being equal to r. This theorem says nothing about that. For each fixed r less than capital R, the series converges uniformly. If you don't know what converging uniformly means, I'm not going to get into it, but just know that it's like the ultimate form of convergence that you would want. Limits of things that converge uniformly uh, often share the property of the sequence. So if you have a sequence that converges to some limit z, and you know something about the sequence elements, such as maybe there's a functions and they're all analytic, right? Then uniform convergence will usually guarantee that the limit is also it also has that property, so it would also be analytic. Right? So same thing for continuity of functions and all these nice properties you can have in the sequence will get to uniform convergence. Okay, so this holds true for modulus of z less than or equal to r. So let's just draw a quick picture here of what this theorem says. Let's take our origin to be right here. Then we have two circles. That's a terrible circle, but we'll go with it. And the first one has radius r. Sorry, little r. And the second one has radius capital R. And this capital R is the radius of convergence. That's what this thing is called. And inside of that radius of convergence, so for any little r less than that, we have uniform convergence. So uniform convergence in here. And then outside of, so we have outside of little r, we have convergence. And then outside of capital R, we have divergence. And then at R, it's inconclusive. Don't know. Okay, so you might remember something like this from your second calculus course when you deal with like power series and things and real variables. Right? The only difference here is that now our domain is the complex numbers. And so the radius of convergence isn't just telling you something about an interval anymore, right? Now it's telling you something about a disk in the plane. Okay, so let's go ahead and prove this. So if the modulus of ak times little r to the k is bounded for some r0, then it's bounded for all r between 0 and r0. Now define r, which is going to be 0 or between 0 and infinity, to be the supremum of the lowercase r's such that ak r to the k is bounded. Then ak r to the k is bounded if little r is less than big R, just by construction. Like this is how we're defining capital R. While if little r is bigger than capital R, then there's a sequence, a subsequence, I should say, which diverges. Right? So we're choosing this capital R to be the supremum of all the r's for which this thing is bounded. So if little r is bigger than that, then there must be a subsequence that diverges. If if modulus of z is bigger than capital R, then ak z to the k does not tend to 0. right? Because that would be an example of an R which is bigger than capital R. And so there must be a subsequence that diverges. And so this thing's not going to tend to zero. And we know that convergent sequences, the terms in the sequence will converge to zero. So this tells us that the power series diverges. So on the other hand, if R is less than capital R, we can choose an S such that S is between little r and capital R. And the sequence modulus of AK, S to the K, is bounded. Let's say, let's give that bound a name. Let's call it C. And this is for K greater than or equal to 0. Now, if the modulus of Z is less than or equal to R, well, then we can write the modulus of AK Z to the K. So these are the terms of the power series. It's less than or equal to modulus of AK R to the K by this assumption, which is equal to modulus of AK S to the K R over S to the K. I've just inserted S to the K over S to the K. And this is less than or equal to C times R over S to the K. Okay, so set MK to be C R over S to the K. And then we're going to apply Weierstrass M test, which is, let me scoop this up from our Calculus 2 course. So if you don't remember, the Weierstrass M test looks like this. If these MKs are greater than or equal to 0, and the sum of the MKs converge, and you can bound, I'm going to write it like this. You can bound your series terms above by MK, where this is the series we're considering here. Then this guy converges uniformly. So we're going to use this M test from calculus, since, well, this guy converges because R is less than S. So this is just a geometric series. Right? So we get convergence there. That implies by the M test that the sum converges uniformly. This is for modulus of C less than or equal to little r. And since we're dealing with the absolute values here, we also get absolute convergence. And so that completes the proof. Okay. So all that is just to say that we have this nice property, the power series, where we can draw a disk like this, and it has some radius of convergence such that on the inside we get convergence, and in fact uniform convergence, but on the outside we get divergence, and on the boundary anything can happen. So maybe a quick example is worth doing, or at least pointing out. The obvious one is the geometric series, right? This guy, we know from calculus this converges for modulus of z less than 1. So the radius of convergence is 1. And in this case, it does not converge for modulus of z equal to 1. Right? Okay. Another example, which is less trivial, is z to the k over k squared. And this one converges uniformly for modulus of z less than or equal 1. And this follows from Weierstrass and test. And the dominating term here is mk equals 1 over k squared. So if r is bigger than 1, then r to the k over k squared diverges. And we just take the limit. So we get divergence for modulus of z greater than 1. So that tells us that, in fact, r is equal to 1. Okay. So the boundary of that requires a little more care, and I think I'm going to go ahead and forgo doing that in the interest of time. Let's move on to the next theorem. Suppose you have a power series with radius of convergence. I'm going to abbreviate that to ROC, r greater than 0. Then the function defined by the power series is in fact analytic on the disk of radius r. Okay. Let me note first that before I prove this, well, actually, I think let me just note quickly before I prove this. I mean, the proof is not hard at all. The derivative of f will be given by the sum from k equals 1 to infinity, k, ak, z to the k minus 1, and so on. What I mean by that is derivatives are done term-wise. The way you're used to differentiating power series still works. The coefficients are given again by 1 over k factorial times the kth derivative evaluated at 0. Okay, so let me go ahead and prove the theorem. It's not long at all. So the partial sums of the power series are polynomials. Polynomials are analytic. The series converges uniformly. series converges uniformly for modulus of z less than r. And so since the series is the limit of the partial sums, that implies that the limit is also analytic. So f is analytic. Okay. So we have a sequence of partial sums. Each partial sum is a polynomial, so it's analytic. And we know from our previous theorem that for modulus of z less than r, this power series converges uniformly. And then the uniform convergence is our very strong form of convergence that guarantees that the limit is also analytic because of the sequences. Okay, so we care about power series because they form a large class of analytic functions, right? And one question we can ask is, well, how can we compute R in general? Is there a nice way to do that? The answer is yes. You know, same tricks you use in ordinary calculus. Right? We have this ratio test. I won't bother proving. It's just the same proof as in real analysis. If the ratio between the successive terms has a limit as k goes to infinity. So we want this limit to be less than or equal to infinity. Then the limit is in fact the radius of convergence. So r is equal to the limit as k goes to infinity, modulus of ak over ak plus 1. So if you remember back to Calc 2, where you had to do these different tests to figure out whether or not your series converged, and you remember the ratio test was probably the one you went to first, and your professor probably engineered problems where the ratio test would give you 1, so that you didn't know whether or not your series converged, and you had to use some other test which is more complicated. Yeah, okay, so this is all the same. We also have, oops, we also have the root test, which basically just says that r is also equivalent to 1 over the limit as k goes to infinity of the kth root of modulus of ak. These are the two main ones that get used a lot. There are other tests we can use, but these are the ones that are probably going to serve us pretty well. Okay, so we have seen that power series are analytic in the last theorem. And what we'd like to know is whether or not the converse is true. If we have an analytic function, can it be written as a power series? And the answer is indeed yes. So suppose f is analytic for z in the disk centered at z0 with radius rho, then f can be represented by a power series. Where the coefficients are the kth derivative at z0 over k factorial for k greater than or equal to 0, and where the power series has radius of convergence, r, which is bigger than or equal to rho. We also have that for any fixed lowercase r, where r is between 0 and rho, we have the Cauchy integral formula tells us that this can be computed as 1 over 2 pi I, the integral on the disk centered at z0, radius r, of f zeta over zeta minus z0 to the k plus 1 d zeta. So this is basically just the Cauchy integral formula. It's the derivative version, right? So you're just plugging that into this guy. And further, if the modulus of f is less than or equal to capital M for z on the disk centered at z0, radius r, then the coefficients are bounded above by m over r to the k. And that just follows from this formula. Okay. So I'll prove the parts I haven't pointed out. For simplicity, let's just set z0 equal to 0. Right, we can always do that with the substitution, so not a big deal. Fix z such that modulus of z less than lowercase r. For the modulus of zeta equal to r, we have 1 over zeta minus c is 1 over zeta, 1 over 1 minus z over zeta. This is equal to 1 over zeta, and I'm going to use the geometric series now. Right, so remember, modulus of zeta is r, and so modulus of z will be less than modulus of zeta. So this geometric series does indeed make sense. But this is equal to the sum from k equals 0 to infinity of z to the k over zeta to the k plus 1. And this series converges uniformly for modulus of zeta equal to r by our theorem. Hence, f of z is 1 over 2 pi I, the integral over modulus of zeta equals r. So this is the circle radius r, f of zeta over zeta minus c d zeta. That's my Cauchy's theorem, or rather Cauchy's integral formula. And this is equal to 1 over 2 pi I, the integral over the circle of radius r. And I'm going to insert this sum. Right, this is the sum I just derived up here. I need my d zeta. And now I can pull this sum outside because it converges uniformly. And the z is irrelevant to the integral, which is over zeta. And so this must be equal to the sum over k, ak, z to the k. Thus, f is represented by a power series which converges for modulus of z less than r. Okay, so this is the power series and these are the coefficients. All right, so we have both directions. This is great. If you have a power series, it's analytic, and if you have an analytic function, well, it is in fact a power series, or at least it can be represented by one in some region. So I should mention a couple of remarks here. The first is that an analytic function on a disk is completely determined by its value and the values of its derivatives. At the center. Right, so if I have an analytic function f, it can be written as a power series where the coefficients ak are fk z0 over k factorial z minus z0 to the k. So what determines this guy? Well, it's the value of each of these things. And what are those? Well, it's just the value of the function and its derivatives at the center of the disk. Okay. So that tells me I have this corollary. If f and g are analytic on z minus z0 less than r, and if all of their derivatives are the same just at the center of the disk, then it follows that f is equivalent to g for z minus z naught less than r. Okay, so if I have two analytic functions and all of their derivatives agree just at the center of the disk, then in fact they're the same on that disk. So the other thing I want to point out is the radius of convergence is the distance to the nearest singularity. I haven't defined what a singularity is yet, so I want to mention this so that we can come back to it later when we do talk about singularities. But essentially, these are points where your function does something you don't like. You know, it blows up to infinity, or it's discontinuous. Has a removable singularity. Yeah, so these things you don't like are called singularities. We'll get into that more concretely later. But this gives me a corollary. Suppose f is analytic. That means it can be written as a power series. Yeah, by the way, you remember we defined analytic as meaning a function which is complex differentiable and which has a differentiable derivative. and that last or continuous derivative, and that last assumption was what turned out to be redundant by Gauss-Sotz theorem, but that condition that the function is complex differentiable, uh, being being analyticity, must be equivalent to the existence of a power series representing the function f. So we have two equivalent definitions of analyticity is what I'm trying to say. It's complex differentiability, and then it's also ability to write the function as a power series. And this does not hold true in real analysis. Okay, but anyway, suppose f is analytic, then r, radius of convergence, is the largest number such that f extends to be analytic on, well, the disk of radius r. And by this first remark up here, notice that this implies that that extension is unique. Okay. So just as a quick example, I want to mention 1 over 1 plus z squared. So this is equal to the sum from k equals 0 to infinity of minus 1 to the k x, I should use z here, z to the 2k. And this has a radius of convergence 1 because this function has singularities. This function is singular at z equals plus or minus I. The power series is centered at 0. The singularities are at plus or minus I. Let's draw. Here's I, here's 0, here's minus I. The distance to these singularities is 1. And so that's what R is. Okay. All right, so let me get a little further here before we stop. Let f be analytic at z0, and suppose f of z0 is equal to 0. But f is not identically 0. So identically 0 just means that the function itself is not the 0 function. We say f has a 0 of order n at z0 if f of z0, f prime of z0, and so on all the way up to the n minus 1th derivative are all equal to 0 at z0, while the nth derivative at z0 is non-zero. But this happens if and only if f of z can be written as a n z minus z0 to the n plus a n plus 1 z minus z0 to the n plus 1, and so on, right? How do we know this? Because, well, if we write f in its power series form, we know that all of the derivatives up to and not including n are 0, and these form the coefficients, except for a factorial. Right? So all of the first n coefficients are all 0, And so we must have this form. Okay, so this is just sum k equals n to infinity of a k z minus z naught to the k. Well, then that tells me that f of z must be equal to z minus z naught to the n times h of z. So what I'm doing here is I'm pulling out these n factors of z minus z naught, where h is now analytic. And h of z0 is equal to an, which we note is not equal to 0. So the idea is if you have an analytic function that has a 0 of order n, you can pull out those zeros of order n just as factors of z minus z0, just like you would a polynomial. And then what's left is something that does not have a 0 at that point. So you're kind of, this is like the complex analytic function version of fundamental theorem of algebra. Okay. Turns out that the converse is also true. If you have an analytic function of this form, then it has a 0 of order n. I mean, that's just the trivial direction. Some terminology. 0 of order 1 is called a simple 0. And a 0 of order 2 is called a double 0. And you can go on, triple 0, quadruple 0, and so on. But yeah, the weird name is simple here. Okay, here's an example. The zeros of the function sine of z are at n pi, where n is an integer. And the derivatives are cosine of, well, we're going to evaluate at n pi. Right? And this is minus 1 to the n. Right? So it's plus or minus 1, which we note is not equal to 0. So that means that we have a 0 at the evaluation of the function, but non-zero for the first derivative. So what we have is these are all simple zeros. And so this tells us that sine of z can be written as z minus n pi times some analytic function, h of z. Okay. All right. So now I'm going to talk about isolated points. I'm going to introduce the uniqueness principle, and I won't prove it today. We'll prove it next time, but I want to at least mention it. But first, I need just a little bit of terminology. We say that a point z0 in some set E is an isolated point. Of E if there is a row greater than 0 such that z minus z naught is greater than or equal to rho for all z and E other than z naught. So if I can find a point such that every other point in the set is at least some distance away from that point, then that point is isolated. So picture. Suppose you have, okay, hey, how about this? Here's -1, here's 0, and then we can draw several other points here, so on. And I'll draw a line here. Each of these points is isolated because there's some distance between it and every other point in the set. But these points on the line here are not isolated because there are points arbitrarily close to it. Okay. Okay. So this example that I'm trying to illustrate here that I've drawn poorly would be -1 to 0 union the set 1/n and greater than or equal 1. And all of these points. So basically this part would be isolated. All right, so let me state the theorem. Actually, this isn't the uniqueness principle. It's the theorem that implies the uniqueness principle. If D is a domain and F is analytic on D and not identically 0, that just means F is not the 0 function, then the zeros of F are isolated. So if your domain, if you have a domain, F is analytic and not identically 0, then the zeros of F are in fact isolated, like they are in this example. And what that is going to tell us is this nice corollary, which goes by the name uniqueness principle. I've also seen it called the identity theorem. If F and G are analytic on a domain D, and if F is equal to G for Z belonging to a set that has a non-isolated 0, actually you don't need 0 there, you need a point, then F is equal to G on D. Right, yeah, okay. So if you have two functions that are analytic on some domain, and if those happen to be equal to each other for Z belonging to a set that has a non-isolated point. So Z doesn't have to be the non-isolated point. Z just has to belong to a set that has a non-isolated point. So an example of that would be the real line. Then in fact, F is equal to G on the entire domain. That is implied by this theorem, which we're going to prove next time. So that's where I'll go ahead and leave off today. All right. Any questions?